Hey folks, so we're back to think about depth first search. I left you last time with a little bit of a cliffhanger of what is depth first search used for, right? What's the point of depth first traversal, depth first search? Well, to answer that, I went ahead and copied forward the tree we got from last time. If you're not sure how we got these numbers, the start and finish times, or the connections, go back and review the last lecture. But what we're going to do now is use that tree specifically to classify every edge. And some edges in particular are going to be of interest to us. But I think I could do it off of this guy. It turns out you can do it using the numbers, the discover finish time numbers. And if you're doing it in a computer, obviously that's how you do it because you can't do it visually. But as a human being, it's a little bit easier to just look and figure out which of these edges has occurred based on the shape of the tree. So I'm going to go ahead and draw in, these are going to be the tree edges, the blue highlighted ones. Those are the edges I'm drawing in right now, and specifically I'm drawing the tree rooted at A, with all of the other sort of nodes hanging down from there. So let's see, we have F. I have to pull this up a little bit. So I have F. Below F we have two paths. We have one side we have G, and then below it we have H. And then the other side of F we have, this is I, and below I we have D. Right, so all I did is conceptually pick up the tree starting at A, and kind of this is how all of the stuff would dangle down from A, all the stuff that's attached to it. Okay, so all those highlighted edges, those ones that we originally had in blue, these are tree edges because, well, they're literally form the tree. That one I think is easy. Now, there's going to be three kinds of other edges. So let me give you maybe an easy one to recognize to start with. Let's see here. A good one. How about A going down to D? All right. A going down to D. This is this edge. That's not a tree edge, right? It wasn't part of our initial depth first search exploration, but it's an edge going from a node down to a node that descends from it. So this is a forward edge because you're going from an ancestor to a node that descends from them. And maybe a good comparison then to that would be, let's do D to E. How about this edge? Well, D and E, let's see, let me find them. D is here, E is here. Again, it looks like it's going to be an edge that's going between a descendant and an ancestor, or an ancestor and descendant. But unlike the last one, the edge goes from D back up the tree. Right? From D back up the tree. So you're going from D back to what was to be their parent, their grandparent. So we're going back to their great-grandparent, basically. And that is a back edge, because you're going backwards up the sort of tree of ancestors. Same deal then with B. This is going up the tree. So what we just did are all the edges involving D. All right, now all the edges involving D have been classified. Back edge, two of them are back edges, one's a forward edge, and then this I to D was a tree edge. All right. Let's see. Take a moment here. See if you can spot any other forward edges or back edges. Yeah, look at the remaining edges, see if there's any there, forward or back edges. All right. So looking at it, I see E to G. This connection here is going down the tree, right? It's easier to see here, I guess, right? E to G goes forward down the tree. So that might be one you saw. Let's see, any other ones? Oh, here's one. H to F. H to F is a back edge because it's going back up the tree. Very nice. So looking at it, those are all of the forward and back edges. Now, obviously there's some unclassified edges. So you might be like, wait, what a minute. E and C or I and H. Those are our third kind. If it's not a relationship between a descendant and an ancestor, it's a cross edge. So E to C, this one's an obvious one because of how they're shaped in the tree. E going to C isn't going up to like a grandparent or a great-grandparent. It's going to like a sibling node. Yeah. E is going across the tree, not to a descendant of them or an ancestor of them, but like a parallel branch. And then that's also true even if they're not on the same level of the tree. So like I and H here, for example. I connects down to H, yep, correct. So that's going across the tree, not going, down to a descendant or up to an ancestor. It's going down to, I guess this would be sort of the, aunt, uncle node to H, right? It's their parent's sibling. Something like that. Okay, so there's all your edge classifications. These are going to turn out to be useful for us in what we want to do with our depth first trees. But I'm going to put that on the back burner for a moment. We have some other things we need to think about first. Okay? So hopefully that makes sense. I'll come back to this page in just a few minutes. Before that, get this centered on screen. Before that, I do have a little tangent I need to go on to make this thing make sense. And I think it's stuff that we've already kind of talked about, and you've probably, you've likely seen if you've sort of thought about graphs in the past, which is paths through a graph. So far, we've been thinking about taking like single edges, but you could take a sequence of kind of edges. So a path is a sequence of vertices where each pair of adjacent vertices in that sequence are connected by an edge, right? So if you have V1, V2, V3, V4, and so on, all the way until you get to V K plus 1. Everybody, this is V4. That was V5. That was V5. Okay, so everybody along that path, pairwise, adjacent pairs are connected. Okay, so we can start, the idea is we can start in V1, and by following multiple edges, we can get to VK plus 1. That's the intuition here. All right, so let's just draw like a sample path here. I don't know. Doesn't really matter too much where our path goes. Let's say it starts from A. So I start in A, I go down to D, I go down to E from there. I don't know, let's say we go to F, and then from F we go up to I, and I we go to D, and then D we go to B. Like so. So that would be a, drawing in the edges so you can see the path it's taking. That would be a path through the graph, and let me go ahead and write down that sequence of vertices. A, B, I got it wrong. A, D, E, F, I, D, B. I think that's right. A, D, E, F, I, D, B. Okay. So this path, first off, has a length associated with it. That's something we're kind of interested in. This is a length of, well, 1, 2, 3, 4, 5, 6 edges. X equals 6 edges, aka if you look, it's 1, 2, 3, 4, 5, 6. One less than the number of vertices. Okay. That'll be true kind of in general for these guys, because you're connecting them right across the adjacent pairs. All right, so looking at this guy, you know, if you're on a map, say you're on like a online map tool, and you're looking for a path to go somewhere inside your city, and you want to go from A to B, for example. Is there anything weird about this path? Anything that stands out as bad? Well, one thing you might notice is we could have just gone A directly down to B. So there's a much shorter path available to us. Okay, so that one I think is probably stands out to you. But even if we remove this edge, even if we discount that edge from consideration, I think looking at this, something might stand out to you as silly about how our path works. Our path goes through D twice, right? We went through the intersection D 2 times in order to reach our destination. Well, why didn't we just turn in the correct direction originally? Going off in this extra loop didn't seem to benefit us at all. So if Google Maps, or whichever your favorite sort of online tool is, gave you this path, you'd probably be mad, all right? So the kind of path we're thinking about then, where there's no self-crossing, is a simple path. And a path which minimizes the distance you need to travel is called the shortest path. We'll think about shortest paths, but not this time. So we'll come back to that problem. Simple is kind of what we're kind of interested in for the moment here. The simple paths. Let's actually draw an example simple path. I don't know, just a real simple one here. No pun intended. Let's say we went from E to G to H to F. Again, there might be shorter paths that go the same places, but you can just look at this path and you can see nothing is duplicated in it. Yeah, there's no duplications of vertices. So this is a simple path. Whereas here you can look and see immediately this is not simple. And let me write that. This guy is not simple. This guy is simple. All right. So there's a couple examples of paths. Again, bear with me if you've seen paths before. I do have one more path I want to show you on this. let's say we took the following path. Let's go from I to H, from H to F, from F to I. Okay, so let me write that down. So we started at I, H, F, and then we went back to I. All right. So this guy right here is obviously a path. This is a perfectly valid path, but it also has a special name. Paths which start and end at the same location are called cycles. So this is a cycle specifically of 3 edges. So this is a 3-edge cycle. You could think about it like a bus that starts at I, goes to H, goes back to goes to F, goes back to I, and then restarts its bus route. All right, that would be a pretty natural thing to want. So your bus goes in a loop and can continue along its bus route after sort of completing the loop. Questions? Sort of that makes sense. I do have a question that comes up to me, which is this simple? Is this a simple path? Well, by definition, I guess you would say probably not. I have a repeat, so it doesn't seem like it's simple. But also, cycles always have a repeat. So, right, a cycle is always going to repeat on its first and last, at least. So we're going to extend our definition of simple slightly to include simple cycles. So a simple cycle is one where all the vertices except for the starting one and the last one are distinct from one another. These two will not be distinct from one another. Just in case you're curious, what does a cycle that is not simple look like? A non-simple cycle? So you could have a cycle that kind of goes maybe like in this figure 8 motion. So let's say you start at A and you get back to A, but somewhere in the middle there's a node you visit twice, right? That would be a non-simple cycle. I don't know if I graph this is complex enough to draw that in there. I'd have to stare at it for a while. But yeah, so there's a non-simple cycle, just as an example. Okay with that? Cycles, simplicity, paths, all that good stuff. So more just terminology stuff. If you're thinking about ondirected graphs, we're going to say an ondirected graph is connected if for every pair of vertices there is a path from the first vertex to the second vertex. And because it's ondirected, there's obviously going to be a reciprocal path, one going from V to U as well. Let's draw some graphs here and decide if they're connected. Keep the problem not too tricky here. So how about this guy? My C node's a little small. A, B, C, D. Looking at this guy, is there a path from every vertex to every other vertex? Well, yes. There is no direct connection between some of them, like A and D have no direct connection, but you can reach D from A by going across 2 edges, right? Same for C. If you wanted to go from B and C, you could get to B with 2 edges. Yeah. So this is connected. What would a non-connected graph look like? Well, suppose you have a graph that looks like this. So this entire thing is G1, this entire thing is G2, right? Feel free to give them names, A, B, C, D, E, F, G, H, I. I know those are small, so if you can't see it, don't worry. Names don't matter too much here. The real key is that if I'm starting at A, there's no way I can get to C. Or if I'm starting in C, there's no way I can get to G or to B. They're like islands. And actually, we have a special name for that. So these are considered connected components. So there's 3 connected components. That is, if you kind of expand out so that you can explore everything that's reachable from some node. These are the guys that are all reachable from one another. These are reachable from one another. These guys are all reachable from one another. But there's 3 different kind of islands. So this is not connected. Not connected. Straightforward, I think, to see. Okay. So you can think about, if you want to think about more applications of depth first and breadth first search, you could think about testing for connectivity. Go back and think about how you would modify the algorithms we saw to detect if you ever are ever in the case where there are nodes that are not part of a single connected component. There's some nodes that are not visitable maybe from your starting point. That would be a nice little extra problem to think about. But yeah, thinking about strongly connected components, this is just for directed graphs. We extend the idea to explicitly require the path to go from V to U and from U to V and V to U. So, for example, say my graph looks like this. Say this is A, B, C, D. Is this a connected, is this a strongly connected graph by this definition? From every vertex, I can go to every other vertex and back. Well, stare at it for a moment. As always, pause the video if you need to. This is not strongly connected. Strongly connected. The reasoning being that if you think about it, D can reach everybody, but nobody can ever reach D. So D is kind of its own island, and BC, A, B, C can all reach each other. So they're kind of like their own island. So there's 2 connected components. 2 connected components in this graph. All right. And then if you want an example of a strongly connected graph, yeah, could have something like this. It doesn't matter too much sort of how it's specifically drawn, kind of just throwing in extraneous edges. But I claim no matter where you start, I'll get my hand out of the way here. So I claim no matter where you start in this graph, no matter where you start, you can reach everywhere else, and everywhere else can reach you. Right? So try that out yourself. This graph, just sort of a more complex version. If you want a simple version, this guy without D is a strongly connected graph. Okay. All right. This guy is strongly connected. Okay. I know, but now you're wondering, where does depth first search come into play? Almost there. Got one more slide, I guess, to get through before we'll be back to depth first search. All right. Now that we have specified those, it turns out you can use those things we just specified to describe a bunch of different data structures, specifically particular kinds of graphs. For example, if you have an ondirected graph, which is completely connected, and there are no simple cycles in it, this is called a tree. So acyclic is a new word. We didn't define it on the previous page, but acyclic means no simple cycles, aka no going in a loop back around, not allowed. Okay, so in this case it's ondirected. Right, so we're not allowed to have a cycle, so I can't connect these guys, for example. That would make a cycle. I could make some more nodes, connect those like this. That's allowed. I can't make disconnected parts. Like that would not be allowed. So I gotta connect that to all the other parts from my graph. Okay, so have fun. Draw kind of some graph that meets this criteria. And then that thing you have drawn, I claim, is a tree. Yeah, looks just like how we think of trees in computer science, right? No, not really. But this is mathematically a tree. Now, usually in computer science, we have a couple other properties. We want rooted trees, and we want binary trees frequently. But this guy doesn't enforce them, right? So it doesn't enforce these guys. But you could have had those in. Okay, so these guys are kind of like trees without the root node, without restrictions on like how many children you can have, right? Okay, what happens if we change the definition a little, just for fun? Let's say we tweak it. We take this undirected connected acyclic graph, and we just say, let's get rid of connected, right? Connected goes away. What changes? Well, if you sit down and you try and draw it, you're like, okay, well, I still can't make I can't connect here because that would make a cycle. So I can still do this kinds of stuff. What's changed? Well, now we can have disconnected portions to our graph. And so this is a collection of trees. Each of these guys individually is a tree, and then this collection of trees has a cute name. It's called a forest. I think I mentioned this last time as well. So this is a forest of trees. Very cute, and this is actually a handy data structure. This name does show up a bit, and there are applications. In particular, we might think about this later. I need to see how much time we'll have. Union Find Data Structure, UFDS, uses forests. So if you're looking for an application, there you go. Spend a few minutes Googling UFDS, Union Find Data Structures, and try it out. I'll write up Union the whole name. So check those out if you're interested. But that's not really why we're here. Instead, what we're really interested in comes from making another change. I'm going to keep the connected gone, but I'm going to change onDirected to directed. Otherwise, still acyclic, still a graph. All right, we're going to create something new. And, well, now it's directed, so I can have directed connections, like that, or like this, but I can't have a cycle. You know, that's the real key, is I can't have a cycle. And so I can have sort of these guys running in parallel, but I can't have a way to go back further up this guy, right? I can't have a way that allows me to return back, but I can kind of have a, I think of this like a river. It has almost like a flow to it. The river can branch, right? And the river can merge, but it can't flow backwards. All right? So yeah, draw your own example if you're so inclined. Notice you could have parallel disconnected parts, right? That is technically allowable. So this is like having two rivers sort of running next to each other that don't really share a source or a sink or any contact. Yeah, you could have something like that. Okay. Makes sense. So this is the data structure we're interested in. This has some really cool properties. It actually does have some useful applications. Before I get to that, though, I guess I should talk about the name. I skipped saying it because I wanted you to think about it. It's DAG. Any idea why it's DAG? Oh. The reason is pretty simple. It's because it's a directed acyclic graph. DAG. Cute name. So there you go. There's what we're really interested in. We've generated that. But we're going to be interested in the path stuff and the connectivity stuff again in the future. So that discussion isn't wasted. We'll just revisit it in a bit. Now we're ready to talk about a application. And maybe at this point, you want to see an application, but you're kind of skeptical about this idea that DAGs are useful, right? That these things are practical in some way because they don't look immediately useful. They don't behave like the graphs we have been using quite, not having cycles and such. But I can pretty much guarantee you've seen a DAG. Or something essentially that's a DAG. So this might not be the most up-to-date listing on the UTSA website, but you've probably seen something like this when thinking about course registration. This guy right here is a graph of prerequisites to register for courses. So, for example, this is the undergraduate catalog. We have like algebra and pre-calc, which are assumed you took them in like high school or such. And then we have calculus 1, calculus 2. Those guys have sort of these arrows descending down. So like calc 1 is required for discrete mathematics. And then calc 2 is required for math foundations. Intro to CS, the intro programming class 2, is required for both of these guys, so it's got an arrow. Data structures, right? That's required for a bunch of stuff. You can see these kinds of arrows merging and coming together. And I claim that it's a DAG. So you might question that then. You might say, okay, well, even if I do recognize this, how do I know it's a DAG? Take a moment. Think about this yourself. Why do I know this is a DAG or should be a DAG? So what if it wasn't a DAG? Then there's a cycle somewhere, right? There's a cycle somewhere in our graph. But if there's a cycle, then I have a course A, which requires you to take course B. Is required for you to take course B. So if you want to take course B, you need to take A first. Well, if you want to take B, let's say you need to take B in order to take C, and then you need to take C in order to take A. Right? A, this guy is required for B. B is required for C, and C is required for A. There is no way to ever take any of these courses. So if your graph was not a DAG, that almost assuredly means something has gone horribly wrong, and you would want to report that. All right? And otherwise, though, it should be a DAG. Neat, right? Think about that. Make sure that makes sense. And finally, I've gotten to how we're going to apply depth first search. There's a lot of things you can use it for. I'll show you some other cool problems probably to use these. But this one is really a nice, elegant solution. Suppose you're running a university and you want to identify whether something's a DAG. Well, to determine if your graph doesn't have cycles, it turns out that's the same as doing a depth first search and seeing no back edges. Let me pull this page back up for a moment. This guy. So back edges imply a cycle. So looking at our picture here, back edges go higher up in the graph. So if you go back up to a grandparent or a great-grandparent, obviously you can still descend from your great-grandparent back to yourself. So a back edge inherently implies a cycle. This is not true with forward edges. Forward edges are just skipping further down the river or further down the family tree. They're not going back in time, they're just kind of skipping a generation. Cross edges, similar. Not going really backwards in a way where you can return. They're just kind of zigzagging back and forth across the family tree. Right? Rivers merging together and splitting. Make sense? Think about it. So back edges, finding a back edge is sufficient to tell you that the graph has a cycle, and it turns out it's also necessary. It's a necessary and sufficient condition to find a back edge to imply a cycle. And I have the proof sketched here. I'm not going to go through the proof sketch because honestly, it's just not that interesting, I don't think. The proof sketch I have here is fairly hand-wavy. I think you can work out the logic yourself. If you want a more formal proof, I think there might be some in the CLRS algorithms textbook, which you might check out. But yeah, so, look at this guy, think about it, that this makes sense, that if you have a back edge, you got a cycle. And if you have a cycle, think about what that implies when you do a depth first search. Draw pictures if you're so inclined. And there is our application for these good old depth first searches. All right. But we're not quite done yet. I've got one more page. Because there is something else that's cool about a depth first search. So yeah, obviously the nodes in the DAG represent events, like taking courses. But really, you're not just interested in how the courses are connected to each other. If you're coming to UTSA, you want to figure out which courses do you take next in sequence, or what's a valid schedule of courses to take. Now, we do that by giving you a schedule of recommended courses to take per semester, but you could also automatically generate a sequence of courses which would not violate the topology of how they're connected. This is a topological sort. So topology has to do with the study of how things are connected together, right? How the elements of your graph are connected together in this case. So, and the topological sort Turns out, use depth first search to find such an order. It's super easy. You just sort the vertices by their finish time, starting with the largest finish times, the things that finish last, going to the things that finished in the smallest finish time. And like that, you have a schedule. Pretty neat. Okay. Again, ponder that. Maybe go back and try that out. Try that out on the graph of classes I have on the previous page, if you want to confirm that for yourself. This is not something I want to dig too deeply into, though, so I'll leave it there. And we'll come back next time, and we'll still be thinking about graph stuff. There's still a bunch of cool stuff we can do with graphs. So hang on. Thank you so much, folks.